All right, homework 22, this is chapter 11. Chapter 11, we only have 3 kind of problems. The end ones might be a little longer. But first of all, they're going to have us fill in a contingency table based on what the expected frequencies are. So it says, to determine a target audience for a new email package, a computer company surveyed a large sample of potential customers, asking each whether he or she uses email on a regular basis. The company considered a regular basis to be at least 3 times a week. The data as summarized in the contingency table below were classified by the age of the respondent and the response to the question. The respective observed frequencies are written in the cells of the table. In addition, 3 of the cells have been left blank beneath the observed frequencies. Fill in the blanks with the frequencies expected if the 2 variables, email use and age, are independent. Round your answer to 2 decimal places. So, here they're just going to have us fill in 3 of them. There are actually 8 that we could fill in when we're doing our contingency table. And in order to do what the value is that goes in that table, is you're going to take the row total times the column total and divide that by the total sample size. So, in order to figure out this first one here for under 18 on a regular basis, I'm going to take my row total, which is the 380, times my column total, which is the 303. So 380 times 303, I'm going to divide it by the total of the sample, which is the 1,000 down there in the corner. And again, you're just going to grab your calculator, take 380 times 303, divide it by 1,000. Oh, 380 times 303 divided by 1,000 gives you 115.14. So my answer there, 115.14. And then basically you're going to do the exact same thing for the other 2 parts. So if I'm going to do this one here, my row total is 380 times my column total. This time my column total is the 291. Divided by 1,000. If you punch that in, you should get 110.58. So this box here, 110.58. And then they're going to have you do a third one. On the third one, now I'm down here for not on a regular basis. I have my row total is 620. Row total 620. My column total, I'm still in the under 18 column, so I have my 303, and I'm dividing it by my total sample size, which is the 1,000 on all of these, since it shouldn't change. So if you punch in 620 times 303 divided by 1,000, you should come up with 187.86. So this box right here, 187.86. So nothing too terrible bad when you're filling in your contingency table, and we're going to do this a bunch through this whole chapter. Row total times the column total divided by your total sample size. So on number 2 there, it says, Mandrake Falls High School is providing a weekend course in laboratory techniques to its laboratory students. Of the 200 students enrolled in lab classes at Mandrake, 73 have taken the weekend course. Mandrake is evaluating the course effectiveness by having its lab instructors record harmful lab incidents or accidents, misuse of lab equipment, etc. The contingency table below gives a summary of the data that has been gathered so far. for Mandrake's 200 lab students. Each student is classified according to whether or not he has taken the lab technique course and how he has performed in the lab. In the cells of the table are represented the observed frequencies. Note that 3 of the cells also have blanks. Fill in the frequencies expected if the 2 variables, status regarding the lab techniques course and laboratory performance, are independents. So, if we took the course, we have no accidents, 1 incident or 2 or more incidents. 31 here, 27 here, 15 here, for a total of 73. Those that didn't take the course, 68 had no incidents, 36 1 incident, 27 2 incidents, and again, if you took 68 plus 36 plus 27, you'd get this 127. Here, no incidents. 31 plus 68 is my 99. 27 plus 36 is my 63. 15 plus 23 is my 38. So they have all of those numbers in there, and they just want you to put in the expected frequency. Expected frequency, then, we're going to take our row total times our column total divided by the total sample size. So on the first one, the first blank here, I'm filling in this box right here. My row total is 73. My column total would be 99. Total sample size, the 200. Again, just punch that into your calculator. 73 times 99 divided by 200 should give you 36.14. 36.14. On my next box is down here in my second column, or my second row. I want to take my row total, 127, times my column total, 99, divided by my sample size, which again is going to be my 200. Just going to grab my calculator. 127 times 99 divided by 200 should give you 62.87. And the third box there we want to fill in. This one here, we're going to take our row total, which is 127, times the column total, which is 63, and again divide by the sample size of 200. And so we should get 40.01. So on number 3, doing the same thing. Westminster Financial has released a summary of investor and investment packaging information from the past fiscal year. During this time, Westminster provided a choice among 12 pre-designed investment packages, which are classified into 3 categories according to riskiness: risky, moderate to mixed, and conservative. Suppose we're interested in the possible relationship between the age of an investor and the riskiness of the investment package she chooses. The following contingency table gives a summary of information released by Westminster regarding age and riskiness of the investment package for 150 investors. In the cells of the table are the respective observed frequencies, and 3 of the cells also have blanks. Fill in the blanks with the frequencies expected if the 2 variables, riskiness of investment package chosen and age of the investor, are independent. So again, we've got our table. They've got them grouped: risky, moderate to mixed, and conservative, and they've also have them by age group: under 35, 35 to 49, and 50 plus. We want to fill in those expected frequencies. So row total times column total divided by total, I can spell, sample size. So on the first box here, I'm doing this one, under 35 and risky. My row total, 35. My column total, 49. And the total sample size, 150 investors were surveyed, right? 150. So if we do 35 times our 49 divided by 150 on our calculator, we should come up with 11.43. 11.43. The next one, way over here where we have the one conservative that is under 35. Evidently the under 35s are more risky. So, our row total is 35. Our column total is 31. And sample size, 150. So 35 times 31 divided by 150 gives me 7.23. And my last one over here at the 50 plus. How many are conservative? So my row total is 55. My column total would be 31. Divided by my sample size, 150. So 55 times 31 divided by 150 gives you 11.37. So here my expected frequencies are what I found. What this really means is if I were going to survey 150 people, I would expect that I would have 11.43 in this category. I actually had 15, but that's what I would expect. Over here, I would have expected to have 7.23, or about 7 people in that category. Down here, I would have expected to have 11.37. I got 11, so I was pretty close on that one. So those are my expected frequencies based on my table. Okay, 4, 5, and 6 are going to be chi-squared goodness of fit tests. It says, executives at the Thinking Channel have decided to test whether the educational backgrounds of the channel's viewers are different from the educational backgrounds of American adults ages 25 and over, as a whole. The executives have following information on the American adult population as a whole, obtained from a recent U.S. current population survey. The highest degree earned, if they had less than a high school education, 12%. If they have less than a high school education, 12% of the people surveyed. A high school education, 25%. College education, 55%, higher than college, which means they have a master's or a doctorate, 8%. So, the executive also obtained from telephone surveys on the highest degree for a random sample of 150 American adults who are Thinking Channel viewers. These data are summarized in the first row of numbers in Table 1 below. These numbers are the observed frequencies in the sample of 150 for each of the degree categories. The second row of numbers in Table 1 gives the expected frequencies under the assumption that the distribution of highest degree earned by Thinking Channel viewers is the same as the distribution of highest degree earned by the American adults as a whole. So they're going to use these same percentages. They're going to assume they're the same. The bottom row of numbers in the table gives the values, and they're using this calculation right here. The observed frequency minus the expected frequency, and I'm going to square that and then divide it by the expected frequency for each degree category. Fill in the missing values in Table 1, then using a 5% level of significance, perform a test of hypothesis that the distribution of the highest degree earned by thinking channel viewers is the same as the distribution of the highest degree earned by American adults as a whole. Complete table 2, which happens to be on the next page because all of this wouldn't fit on one page. Round your responses for the frequencies, expected frequencies in table 1 to at least 2 decimal places. Round your responses for this calculation here in table 1 to 3 decimal places. Round the responses in table 2 as specified. So I'm going to move this up a little bit because we really don't need the word problem to fill in the table, except we need to know these values here. So I'm going to rewrite those values down here once I move this. So, on my table, up on the top, in that other little table, it said 12% were in this category, 25% was in this category, 55% was in this category, and 8% is in this category. Now for a bunch of these, they've already figured it out. If I take 12% of 150, if I grab my calculator, 0.12 times 150 gives me that's what I'm going to figure out. The number I want in my table. So, here is the observed frequency, I should say. The ones I had figured out were these ones. These are the observed ones. These are they're going to use on their percentages. So here, the one they have figured out, 25% of 150. If I take 0.25 times 150, there's my 37.5. 55% of 150. 0.55 times 150, there's my 82.5. So they fill these two in, we want to fill these two in. So in order to fill those two in, here we're going to do the 12% of my 150. I want to know what 12% of 150 is. That's what my expected value would be. 12% times 150, 18. So there should be an 18 in that box. And on the end, we only had 8% of 150. So 0.08 times 150 is my calculation for that box. 0.08 times 150 gives me 12. So, my observed were that 12 people were in this category. My expected at 12% means I thought there were going to be 18. Here my observed was 35. Based on 25%, I would have expected 37.5 people. We obviously aren't going to have a half people, but on my calculation. Here, 88 were observed. Based on my calculation, I would have had 82.5. Once I fill in the expected frequencies by taking my percent times my total, now I'm going to do this calculation right here. So, on the first box here, it says I'm going to take f sub 0, which is 12, minus f sub e, which is my 18, squared, and I'm going to divide it by the f sub e, which is 18. So 12 minus 18 squared divided by 18 is what I'm going to do. And if I do that calculation, I should come up with a 2. Same thing through this box here. Going to use this formula here. So my observed is 15. I'm going to subtract my expected. I'm going to square that, and I'm going to divide it by the expected. Here, when you calculate that, 15 minus 12 squared divided by 12 gives me 0.750. Second page of that. we have to pick out what is the type of the test statistics. Well, according to the name of the directions, we hopefully already know, we are going to do the chi-squared, which is the one that looks like this. We also probably have to figure out the degree of freedom. The degree of freedom on this one is how many different categories we have minus 1. So, the degree of freedom is the categories, the number of categories minus 1. Here we have 1, 2, 3, 4 categories. We have 4 different things. So 4 minus 1 would give us 3, so our degree of freedom is going to be 3. To find the value of your test statistic, this value right here, we're going to add all the numbers in the bottom row up here. So the bottom row was the f sub 0 minus the f sub e squared divided by f sub e. So I'm going to take each of these values and just add them up. So I'm going to take 2 plus 0.167 plus 0.367 plus 0.75. Add those 4 numbers together. If I add those together, I get 3.284 for the value of my test statistic. Now I'm going to do a p-value test. We've done all those testing. We're going to do the p-value test. This is a positive number, good thing, because we like to do p is greater than. P of chi-squared is greater than our test statistic, 3.284, with a degree of freedom of 3 is what we figured out. So again, we have to do that on the Alex calculator. P of chi-squared, that's how that's pronounced. It looks like x squared, but it is chi-squared. P of chi-squared is greater than 3.284 with a degree of freedom of 3. We should get 0.350. Tells us to round to 3 decimal places. So we like to show that third one even though it's a 0. So now we're comparing our p-value to what we wanted to compare to, which on the top, or actually we can see it right here, said we were going to do a 5% level of significance. So, is 0.350 greater than or less than my 0.05? Well, we can obviously see that it's greater, right? 3.5 is greater than 0.05. So, as we did before with the p-values, if my percentage is greater than my level of significance, we want to accept, accept the null. We're going to accept the null. So, they didn't have us write what our statements were. So again, if we were doing our test statistics and it on here, when we did the null we know is going to be equal. The alternative one means it's not equal. The question asks, can we conclude that it is different? Can we conclude it's different? Well, in this case, this is the true statement. This one is not true. The null means it would be equal. The alternate ones, it's not equal. And so can we accept that it's different? Can we accept that it's different? No, because we said it has to be equal. They skipped the step where they had you write the null and the alternate hypothesis because they probably figured by now you knew how to do that. So the null will always be the equal, the alternative one will be not equal. So if it asks me if it's different, I would see, is this one true? No, it's not. That one is not true. All right. So, number 5. Matrimony Monthly is a top-selling magazine that provides information for couples thinking about marriage. Over the years, writers for the magazine have researched just about everything there is to research about weddings. The popular conception at the magazine has been that roughly 50%, we're going to need these percents on our table, of first weddings take place indoors in a church. 30% take place in a building other than a church. And 20% are outside, are outdoors. This past week, the magazine examined a random sample of 250 first weddings and found the distribution given in the first row of numbers in the table below. This row contains the frequencies observed in their sample of 250. The second row of numbers in the table is the frequencies expected based on those percentages under the hypothesis that the popular conception at the magazine is correct. The bottom row is where we're doing our calculation for each of the wedding categories. Now there's some disagreement among employees of the magazine. Some say this sample demonstrates that the actual location distribution of first weddings is different. So again, we're checking different, and so we're checking equals and not equals from that in the magazine's popular conception. Others maintain the sample data according to the magazine's population conception that any differences between the two are due to chance. Fill in the missing values from Table 1, then at a 5% level of significance, perform a test of hypothesis, that is the actual distribution of first wedding locations, matches the distribution in the magazine's popular conception. Complete Table 2. So, going down here, again, we need those percentages, so keep that page handy when you slide down to this table. So, when I get to that table for problem number 5, first thing I'm going to do is write my percentages on top. According to the magazine, 50% were in this category, got married in the church, 30% got married inside but not in the church, and only 20% got married outside when they had their first wedding. So here are the observed data. We want to fill in the expected ones. They already filled this one in for me. If I took 30% of 250, it is that number 75. You could calculate it and find out. 50% of 250 then goes in this first column. 50% times the 250 total, right? 50% of 250 means I would have 125 in this section. For the outdoors we said 20% is our expected, so 20% of our 250, 20% times 250 means we would have expected 50 to be in this category. So now we're going to fill in the calculation from our formula. Again, they already did this one for you. You could calculate it out and see that you do get that same number. They did one of the boxes trying to make it a little shorter. So, observed frequency 141 minus the expected frequency 125 divided by the expected frequency 125. That's my calculation for that box there. Oops, I forgot the squared. Great, I'm supposed to have that squared there. 141 minus 125 squared divided by my 125. If you punch that into your calculator, you should get 2.048. 2.048. On my other one, I'm going to have my observed frequency of 49 minus my expected frequency of 50. I'm going to square that and divide it by the expected frequency, which is 50. So 49 minus 50 squared divided by 50 should give you 0.020. 0.020. Again, because it says to go to 3 decimal places, I like to put the 0 on the end, so I'm showing 3 decimal places. The type of the test statistic, again, is going to be your chi-squared. The degree of freedom your degree of freedom, how many categories you have, minus 1. In this case, we have 1, 2, 3 categories. Either they got married in the church, indoors but not in the church, or outdoors. So 3 minus 1 is 2. We're going to have 2 degree of freedom then. Chi-squared with a degree of freedom of 2. We are going to then find the value of our test statistic. To find the value of the test statistic, we're going to add all the values for the calculation, which means add all these ones in this bottom row. So I am going to take 2.048 plus 3.000 plus 0.020. We only had 3 columns this time, so we're going to add up those 3 numbers. So if we add up those 3 numbers, we get 5.068. 5.068. So we are now on this one going to do the critical value for our test. When we do the critical value, we're not doing the p-test, we're doing the chi-squared test. So we are going to do chi-squared at the 0.05 level of significance with degree of freedom of 2. So on this case, if you calculate that out using your Alex calculator, if you haven't done that already, just giving you a second to get that punched in. Chi-squared at the 0.05 level of significance with a degree of freedom of 2 should give you 5.991. So when I'm testing this one, my critical value is 5.991. I am trying to figure out if I'm in my null section or my alternative section. Again, on my null, the null is the equal to, the alternative one is the not equal to. In other words, does it differ? Is it different or not? So if I check my test value, is my test value smaller or bigger than 5.991? Well, if I look at that, my test value is 5.068. 5.068 would be smaller than 5.991. So I have to do the null because I'm in the section for the null. I have to say that it's equal. Can we conclude that the actual distribution is different? No, I have to say it's equal. It is not different. And so no, I cannot conclude that it's different from the distribution in the magazine. Number 6. Same kind of thing here. Depression and insomnia often go hand in hand, and sometimes it is unclear which of the two should be the primary subject of treatment in an individual suffering from insomnia. Mendoza & Company, a national pharmaceutical firm, has positioned itself as a specialist in the production of both antidepressants and sleeping pills. Mendoza's current business model describes the following breakdown of Americans: approximately 50 million adults suffering from insomnia, 17 use both antidepressants and sleeping pills regularly. 24% use only antidepressants and 15% use only sleeping pills. The remaining 44% use neither antidepressants nor sleeping pills. So in a recent issue of the Psychiatry Journal, Patterns contained a study on insomnia. In the study, 180 Americans suffering from insomnia but otherwise chosen at random were asked about their use of antidepressants and sleeping pills. The breakdown of their answers is given in the top row of Table 1. These numbers are the frequencies observed from the sample of 180 people. The second row in the table is your expected frequencies based on our percentages under the hypothesis that Mendoza's model is correct. The bottom row contains the value that we get when we do our calculation. The observed frequency minus the expected frequency squared divided by the expected frequency. So again, we're going to fill in our table and then answer our questions. And so I'm going to move my table here. Whoa, I jumped all the way to number 4. So on number 6, again, I'm going to slide up this high so we can see both of our tables, but we need to fill in our percentages. And so again, if you go back to the reading, 17% used both, it says. Only antidepressants, if I go to my reading, 24%. Only sleeping pills, 15%. And the remaining 44%, it said, used neither. So again, we're going to do our calculations. Here's the observed data. What is our expectation based on these percentages? Here, these two are filled in. 15% times 180 is 27. 44% times 180 is 79.2. We want these ones. So here, 17% times our 180. If you do 0.17 times 180, you should get 30.6. And then our other one, 24% of 180, so 0.24 times 180. 0.24 times 180 is 43.2. Then they're going to do our calculations here. So my observed frequency, 40, minus my expected frequency, 30.6. This time I'm going to remember to square it, divided by the expected frequency, 30.6. So in parentheses, 40 minus 30.6, then that's squared, and then I'm going to divide by 30.6. And on all these, we're rounding these to 3 decimal places in the bottom row. So we're going to use 2.888 is what we get for our answer. On our other one, our observed was 30 minus our expected, 43.2 squared, divided by the expected, 43.2. So in parentheses, 30 minus 43.2 divided or squared, and then divided by 43.2. We should come up with 4.033. 4.033. So again, on the second table, if we go over to that second table, wants to ask us about the type of test statistic. We know it's chi-squared. On our degree of freedom, the number of categories minus 1. We have 1, 2, 3, 4 categories. So 4 minus 1 is going to give us 3. 4 minus 1 gives us 3. So we have 3 degrees of freedom. So the number of categories minus 1 is your degree of freedom. We had 4 different categories. 4 minus 1 is 3. Value of our test statistic. When we find the value of our test statistic, we're just going to add this whole row together. And so we had 4 different values. 2.888 plus 4.033 plus 1.815 plus the last one, 1.473. So we're adding all the values in that row to get the value of our test statistic. If you add all of those together, you get 10.209. It says round to at least 2 decimal places, which I didn't follow my directions, so 10.21 would also work. But again, it says at least, so if you go farther than 2, it's going to count it correct, it knows. Then we're going to do the p-value on this one. So for our p-value, again, we're testing here between the H0 and the H1. We're going to do p of chi squared is greater than that value, 10.21. And again, you could use 209. P of chi squared is greater than the 10.209. Oh, I forgot my degree of freedom. You'll know, it'll tell you when you type that in on the Alex program. I always am forgetting to write that down for you. But it asks for the degree of freedom, which is 3. So my p-value to 3 decimal places, 0.017. 0.017. So 0.017. We want to compare that to a 10% level of significance, 0.01. 0.017 is just a little bit bigger than 0.01, right? Oh, never mind. I'm not doing 0.01. Ignore me. I'm gone crazy. That does not say 0.1. It says 10. 0.10. So 0.017 compared to 0.10. 0.017 is less than 0.10. Since that is less, my percent here is less than this, we are going to reject the null. Now again, we have to remember that the null is the equal, the alternative one is not equal. So we're rejecting the null. This is not true, which means this one is the true statement. Rejecting the null, we're rejecting that it is equal. That means it's not equal. Can we conclude that the percentages given in the model are incorrect? Can we say they're incorrect? Yes, we can, because they are not equal. That is my true statement. All right. 7, 8, and 9, again, we're doing the chi-squared test of independence. Westminster Financial has released a summary of investment package information from the past fiscal year. During this time, Westminster provided a choice among 12 pre-designed investment packages. Westminster classified the packages into 3 categories according to the risk: risky, moderate to mixed, and conservative. We're interested in the possible relationship between the age of an investor and the riskiness of the investment packages she chooses. Table 1, a contingency table, gives a summary of the information released by Westminster regarding the age and the riskiness of the investment package for a random sample of 150 investors. Each cell of the table contains 3 numbers. The first number is the observed cell frequency. The second number is the expected cell frequency, under the assumption that there is no relationship between the 2 variables, riskiness of investment choice and age of Westminster investor for this past year. The third number is the value that we've been calculating. The numbers are labeled total, are the totals for the observed frequency. Fill in the missing values for table 1. Round your expected frequencies to at least 2 decimal places and round your other values to 3 decimal places using the 0.1 or using the 0.10, the 10% level of significance. Perform a test of the hypothesis that there's no relationship between the 2 variables, riskiness of investment choice and age of Westminster investor for this past year. So, in my table, I have right here. Now we are basically combining what we did on problems 1, 2, and 3 with what we did on problems 4, 5, and 6, and just making one great big long problem. So when we fill in our table, again, we're going to take the row total divided by the column total, or the row total times the column total divided by the sample size. That's going to be the top value. The top value is what we did on problems 1, 2, and 3. Row total times column total divided by my, that was supposed to just be column total, total sample size. So the top numbers are what we did on problems 1, 2, and 3. So I'm just going to go ahead and do the top numbers first. I'm going to do them all in red, and then I'll switch colors for the bottom. So on the first one, my row total is 36, my column total is 50. So 36 times 50 divided by my sample size of 150. If you go ahead and do that calculation, 36 times 50 divided by 150, you get an answer of 12. So 12 goes in your top box. I'm going to go ahead and do the top box on the next one. So again, my row total is 36. My column total is 68 divided by my sample size, which is 150. So 36 times 68 divided by 150 would be 16.32. So 16.32 going to go in that top box. Going to do the same thing here. In my top row there, I'm going to do my row total. My row total is 57 times my column total, which is 50, divided by my total sample size, which is my 150. So 57 times 50 divided by 150 comes out to 19. So 19 would go in that box. And then for the last one on there, top box here, my row total is 57. My column total is 68 divided by my 150. So if you take your calculator, 57 times 68 divided by 150 should give you 25.84. 25.84. All right. The bottom ones we're using that formula, FO minus FE squared divided by FE. So these are the ones we did on problems number 4, 5, and 6. I'm going to switch colors here. So when I'm doing these ones here, I'm going to put them in green. So my observed frequency is 10 minus my expected frequency is 12. 10 minus 12 squared divided by 12 would be the number for the first box. If I do my calculation there, I get 0.3333, so forth and so on. So we're going to put in 0.333 because it says to round it to 3 decimal places. Make sure you don't think these are negatives. There, I'll make it an asterisk instead so you don't think it's a negative. On the next one, my observed frequency is 19 minus my expected frequency, 16.32. I'm going to square that and divide it by my expected frequency of 16.32. If you do that calculation, you should get 0.440. 0.440. Punch that into your calculator. Make sure you know how to get that number. The next box. Here I'm doing this one. My observed frequency is 23. My expected frequency is 19. So 23 minus 19 squared divided by 19. 23 minus 19, and then square that, divide that by 19, and you get 0.842. 0.842 goes in that box. And the last one on that part, we are going to do my observed frequency of 29 minus my expected frequency of 25.84. I have to square that and divide it by my expected frequency of 25.84. So 29 minus 25.84, you're going to square that and then divide it by 25.84. When you do that, you should get 0.386. 0.386. All right, so down on the bottom part then, on the second table, table 2, first of all, it's going to ask you what kind of test statistic you're going to have, and it's going to be chi-squared. Also, every time we have chi-squared, we have to have the degree of freedom. So, the degree of freedom, I'm going to write it up here, is the number of rows minus 1 times the number of columns minus 1. So in this case, I would have 1, 2, 3 rows. So I'm going to have 3 minus 1 here. I have 1, 2, 3 columns. So I'm going to have 3 minus 1 there. Well, 3 minus 1 is 2, 3 minus 1 is 2, 2 times 2 gives me 4 degrees of freedom. 4 degrees of freedom, because I have to take that 2 times this 2 that I got here. Number of rows minus 1 times the number of columns minus 1. The value of my test statistic. If I'm going to find the value of my test statistic, I'm going to add all of the FO minus FE squared over FE numbers. So that means I'm going to take this one plus 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 this one. You're going to add up all 9 of those numbers. So 0.333 plus 0.440 plus 0.060 plus 0.842 plus 0.386 plus 4.216 plus 0.211 plus 1.320 plus 5.055. I got to add all 9 of those numbers up. If you add those numbers up and round to 2 decimal places, you should come up with 12.86. 12.86. This one is asking for the critical value, not the p-value, so we're going to do chi-squared. Chi-squared sub 0.10, or not 0, yeah, 0.10 with a degree of freedom of 4 that we figured out here when we did the number of rows minus 1 and the number of columns minus 1. So chi-squared sub 0.10 with a degree of freedom of 4. Have to do that on your Alex calculator, not your regular calculator. So if you punch that in on Alex, you should come up with 7.78. 7.78 for my critical value. So again, on this one, It didn't start out by asking you what the null and the alternative hypothesis is. On these ones, my null hypothesis is always going to be that it is independent and has no relationship. My H1 is going to be that it is not independent, so has a relationship. I can't spell. I spelled it over there. Ship. Yeah, you fix that and spell it right. So, my null is that it's independent, doesn't have a relationship. My alternative one is it's not independent. Again, when we do these ones, my null is over here. My alternate one's going to be over to the right side. So my critical value was 7.78. 7.78. Is that 7.78 is my critical value? Is the test statistic in the HO section or the H1 section? Well, my test statistic is 12.86. 12.86 would be bigger than that number, so my 12.86 is going to be my alternate hypothesis. So my alternate hypothesis is that it's not independent and it does have a relationship. So it says, can we reject the hypothesis that there is no relationship? Can we reject that there's no relationship? Yes, we can, because we're saying it does have a relationship. So if we're going to reject that it has no relationship, then we're going to accept that it does have a relationship. I hate the one when they use the reject and not the accept the claim. I'm going to reject this one. Can we reject that one? Yes, we can. All right. Number 8. Another one of these big long ones. It says an undergraduate student who won an award for his study of student diagnosed with ADHD, attention deficit hyperactivity disorder. He showed that the students with ADHD performed slightly differently on visual search tasks than did students who didn't have ADHD. The display he used for a search task contained about 20 letters positioned in various locations and orientations on a computer screen. The letters and the positions varied from trial to trial. The task of the participant on each trial was to determine within 2 seconds whether or not particular target letters appeared among the 20 letters. Each trial resulted in either a hit, the target appeared and the participant identified it, or a miss, the target appeared and the participant did not identify it. A false alarm, there was no target but the participant stated there was, or a correct rejection, there was no target and the participant stated this fact correctly. While attempting to get a study published in an academic journal, the student was confronted with the following criticisms. Since he had used colored letters and backgrounds in his displays, couldn't the presence or absence of color vision in the participants have produced some of the effects seen in the data? The student went back and tested his participants for color blindness and reanalyzed the data. So again, we're going to have a contingency table. It gives a summary of 2,000 trials of the experiment. Each trial was performed either by a colorblind participant or a non-colorblind participant. Each cell of the table contains 3 numbers. The first number is the observed frequency. The second one is the expected one that we're going to do some calculating on. And then we're going to have our formula that we have to figure out our observed frequency minus our expected frequency squared divided by the expected frequency. So, whoa, it went all the way back to number 4 instead of number 8. 7, 8. Here's my tables for number 8. So, again, when we do number 8, the first column is like we did, or the first row is like we did on problems number 1, 2, and 3. So, this first one's on the top ones. That looks weird. I'm going to move it down a little bit. This one and this one. We are using our formula, row total times column total. I don't know why I keep underlining that. Divided by the total sample size. So again, I'm going to do all those ones in blue, and so that way you know those are all those calculations. So, first box we have to fill in, our row total is 202. 202 times our column total, 672, divided by our total sample size, 2,000 were surveyed. So 202 times 672 divided by 2,000. If you do that calculation, you get 67.87. These ones say round the first column to 2 decimal places, or the first row to 2 decimal places, the second one to 3. So we're going to round that off to 67.87. I'm going to go over and do this one. This one here, row total is 202. Column total is 722. Divided by our 2,000. So row total 202 divided by column total 722 divided by 2,000. Rounding that off to 2 decimal places, 72.92. 72.92. On the not colorblind, the row total 1,798 times the column total 672 divided by the sample size 2,000. So 1,798, that says 98, yep, divided, or times 672 divided by 2,000 should give you 604.13. 604.13. And then the last box of this one over here, my row total, 1,798. My column total, 722, divided by my sample size, 2,000. I should come up with 649.08. 649.08. Now, the next ones. The next ones is my formula. On my formula that I did, FO minus FE squared divided by FE, right? It's that formula we've been calculating all along. So, on the first one, we have 59 minus 67.87. 59 minus 67.87. I'm going to square that and divide it by the 67.87. Again, these ones we're going to round to 3 decimal places once we punch them into our calculator. So 59 minus 67.87, square that, divide it by 67.87, and we should come up with 1.159. 1.159. The next one over here on the end, we're going to take our observed frequency of 69 minus my expected frequency of 72.92 squared divided by the 72.92, which is my expected frequency. If we go ahead and do that calculation, we should be coming up with 0.211. 0.211. The next one. Our observed is 613. Our expected is 604.13. So 613 minus 604.13 squared divided by the 604.13. The observed minus the expected squared divided by the expected. And again, we're rounding off to 3 decimal places. So we should get 0.130. 0.130. Make sure you're trying to punch those in and come up with the same numbers I'm coming up with, so you have practice putting them in your calculator. Last one here, I am going to go ahead and find the value here. I'm going to take my observed, 653, minus my expected, 649.08. That is squared and divided by the 649.08. When you punch that into your calculator, you should come up with 0.024. 0.024. Second table. Type of test statistic, we now know it's chi-squared, our degree of freedom. The degree of freedom. The number of rows minus 1 times the number of columns minus 1. We have 2 rows, so 2 minus 1. We have 1, 2, 3, 4 columns. So 4 minus 1. So 2 minus 1 is 1. 4 minus 1 is 3. 1 times 3 gives me 3 degrees of freedom. So the number of rows is 2. 2 minus 1 is 1. The number of columns, we have 4 different columns. 4 minus 1 is 3, and then 1 times 3 is 3. The value of our test statistics. Add all the FO minus FE squareds divided by FEs. So I'm going to add 6 numbers here. 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. All of those numbers I circled, we're going to add all of those up. So 1.159 plus 1.780 plus 0.950 plus 0.211 plus 0.130 plus 0.200 plus 0.107 and 0.024. So those 4 numbers that I circled, we're going to add all of those up. That's going to be the value of our test statistic. And if you add those up, you should get 4.56. 4.56 should be your total. We are going to find the p-value on this one. The p-value instead of the critical value. So we're going to do p of chi squared is greater than our test statistic, 4.56. Whoops, I forgot my degree of freedom then. Degree of freedom, 3, right? Don't forget to put that in there. You'll see it when you use the Alex calculator. Chi squared greater than 4.56 with a degree of freedom of 3. P of. So we should come up with 0.207. 0.207 is my p-value, my percentage. Again, when I am looking at this, we have our null, we have our alternate one. This one is that it is independent. This one is that it's not independent. So if it is independent, we have to remember there's no relationship. If it is not independent, we know there is a relationship. So when we do our test statistic, since we're doing the p-value, we're comparing this percent to the level of significance. 0.207 compared to 0.05. 0.207 is going to be greater than 0.05. If my p-value is greater than my level of significance, we accept the null, right? This is my true statement. This is my true statement. So, can we reject? There is no dependence. Can we reject there's no dependence? No, we can't reject that. That's the true statement. The true statement is saying there is no relationship. So can we reject that? No, we can't reject that. Can we reject there is no dependence? No, we can't. We're going to say there is a dependence because there's no relationship. One last one on here. Number 9. Among the huge body of literature on smoking are data detailing the relative successfulness of males and females in quitting smoking. Study of 400 adults ages 20 and older who began various smoking cessation programs produced the data in Table 1 below. In the table, less than 2 weeks means that the individual returned to smoking within 2 weeks beginning the program. Between 2 weeks and 1 year means the individual survived the first 2 weeks but returned to smoking within a year. And at least 1 year means the individual did not smoke for at least a year after beginning the program. Table 1 is a contingency table for whose cells contain 3 numbers. The first number in the cell is the observed frequency, second one is the expected one, and then the third one there we have to figure out using our formula. So the first ones we're rounding to 2 decimal places, the second one's to 3, and then we're going to check at a 0.5 level of significance. Is the assumption that there's no association between the sex and the length of the smoking cessation period. So if we go to our tables so we can fill in our tables. Number 9, that should be the last one. There we go. So on number 9 here, again, we are filling in the top ones using the formulas from problems number 1, 2, and 3. So the row times the column divided by the total sample. So my row total, 245. My column total, 97. Divided by my total sample, 400. $245 times 97 divided by 400. Again, we're rounding the top ones to 2 decimal places, and so we should get 59.41. The next one, my row total, 245. My column total, 208. Divided by my sample size, 400. So 245 times 208 divided by 400 should give you a value of 127.40. 127.40. The next one's moving down to the females. My row total, 155. Almost looks like a 1. My column total for the first column is 97. My sample size, 400. So 155 times 97 divided by 400 should be 37.59 when you do that calculation. 37.59. And then the next one, my row total is 155. My column total is 208. And I'm going to divide that by my 400. And I should come up with 80.60. 80.60 goes there. The bottom rows. The bottom rows we're using our formula. So we're doing FO minus FE squared over FE. So the bottom ones we're going to do in green just so you can see where those came from. So observed frequency is 53. Expected frequency was 59.41. We've got to square that and divide it by the 59.41, which is our expected frequency. So 53 minus 59.41. We're going to square that and then divide by the 59.41. These go to 3 decimal places. So 0.692 should be what you get. 0.692. On the next one, my observed is 134. 134 minus 127.4 squared divided by my 127.40, which is what I got for my expected frequency. So 134 minus 127.4, square that, and then divide it by 127.4. You should come up with 0.342. 0.342. The next one. Our observed is 44. So 44 minus the expected of 37.59 squared divided by our 37.59. The observed minus the expected squared divided by the expected. So 44 minus 37.59, square that, and then divide by 37.59. You should get 1.093. 1.093. And then the next one, my observed is 74. 74 minus my expected, 80.60 squared, divided by my 80.60. So the 74 minus 80.60 squared, divided by your 80.60. And you hopefully come up with 0.540. 0.540 is what you should come up with. Table 2, again, wants to know the type of the test statistic. We know that it's chi-squared and we have to have our degree of freedom. My degree of freedom, the number of rows minus 1 times the number of columns minus 1. I have 2 rows, male or female. 2 minus 1 is going to give me 1. Columns, less than 2 weeks between 2 and 1 year, at least 1 year. I've got 3 columns. 3 minus 1 is 2. So I've got 1 times 2. 1 times 2 then gives me 2 degrees of freedom. the value of my test statistic. When I find the value of my test statistic, I'm going to add all of the ones in the FO minus FE squared over FE. So I'm going to add this one, plus 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 this one. Do not forget to add in the ones you didn't actually calculate. They're still part of your table. They just saved you some work. So I'm not going to write them all down, but on your calculator, 0.692 plus 0.342 plus 0.001 plus 1.093 plus 0.540 plus 0.001. Add all 6 of those up. You should come up with 2.67. We are going to do the critical value. So we're going to do the critical value. We're going to do chi-squared sub 0.05 with a degree of freedom of 2, right? Chi-squared sub 0.05 with a degree of 2. Have to use your LX calculator to do that one. Chi-squared sub 0.05 with a degree of freedom of 2 gives us 5.99 for our test value. So again, HO is here, H1 is here. Our critical value is 5.99. We're figuring out where our test value belongs. Is our test value smaller or bigger than my critical value? Well, my test value is 2.67. 2.67 means I'm in the section with the null, right? So if I'm in the section with the null, this is the independent, this is the not independent. So if it's independent, we're going to say there's no association. If it's not independent, there is an association. So, independent. If you're independent, you're not associating with something else. Not independent, you are associating with something or someone else. So in this case, our null is where we're at. We're going to say that is independent, that there is no association. The question says, can we conclude that there is an association? No, we said there is not an association. So can we conclude that there is one? We certainly cannot. No, there is no association. All right, that's the end of chapter 11.